When we're talking about real valued functions in 3D, functions that take in 3 variables and output 1, we don't have graphs to do that with anymore. We just have no tools available for drawing a graph because we'd need 4 dimensions to do it, and drawing 3 is already hard enough for us. But we still do have access to level surfaces. We can still draw the level surface f of x, y, z is equal to c, and that is very, very similar techniques for drawing it as we had for drawing graphs. We set one variable equal to a constant and draw the slice and put all those slices together to give us some kind of picture of what's going on. Unfortunately, level surfaces start to get very complex very quickly. Most of the simplest functions we'll encounter will have level surfaces that are what are called quadric surfaces. They're the analogs of conics, except they happen in 3D, and there's a huge kind of botany, a huge number of examples of different types. There's cones, there's ellipsoids, there's hyperboloids, elliptic paraboloids, all kinds of stuff. If you like, there's a gallery of quadric surfaces that's available online that give some examples of the type of things that you might see. It was originally developed by Jonathan Rockness, who's at the University of Minnesota, but now it's currently being hosted by Nathan Dunfield. But we can examine a couple of examples. So we might look at the function f of x, y, z is equal to x squared plus y squared plus z squared, and try it to draw a couple of level surfaces. So when we draw x squared plus y squared plus z squared is equal to 0, that shape is a sphere of radius 0 centered at the origin. If we draw x squared plus y squared plus z squared is equal to 1, that's another sphere. Now it's of radius 1. And if we draw x squared plus y squared plus z squared is equal to 2, now that's going to be another sphere. This is going to be a sphere of radius square root 2. And so we can see that the level surfaces, as we change our value of z, we're going to get a sequence of concentric spheres centered at the origin that get bigger and bigger depending on what the value of the function is. That tells us a little bit about what's going on with this function. It gives us some idea of how it's behaving. It's something that gets bigger and bigger the farther away we are from the origin. And it starts to get bigger more quickly because we can see the radius of these spheres get packed closer and closer together. Similarly, we could look at another function of 3 variables, g of x, y, and z. By making a slight change to this function, changing it to x squared plus y squared minus z squared, we change the behavior of the function quite a bit. So now we could look at x squared plus y squared minus z squared is equal to 0, or x squared plus y squared minus z squared is equal to 1, or x squared plus y squared minus z squared is equal to minus 1, and we start to get different behavior depending on these different values. So in the middle, we're actually going to get a shape that's basically a cone that goes straight through the origin and has its top and bottom pointing along the positive and negative z-axes. For the one on top, it looks like we kind of took that cone and thickened it up a little bit. This is what's called a hyperboloid with one sheet. On the bottom, it looks like we kind of took that cone and thinned it out and pinched it off. So we actually get 2 segments. That's what's called a hyperboloid of 2 sheets. And so as we change, we kind of gradually switch from these level surfaces on the top to the middle to the bottom. And so that gives us at least a little bit of understanding of what this function is behaving like as time goes on.